Chemistry, guys. This is going to be the work that we had talked about on page 10 and 11 related to conversions, percent error, accuracy, precision, and scientific notation. So if you're still not quite sure on how to do all these things, this is where you want to be. And go ahead and fast forward through the video to the places that you need, but make sure you're paying attention to the parts that you need help with. So we'll do just a few of these here. Procedures, or stations number 1, 2, and 3. And these are labs that we've done in the past. And this year we just gave you data values. And I'm going to give you different data values here so we have a little bit extra practice. So station 1. We're going to start with a person that is 1.22 meters. We're going to do the conversions into millimeters and kilometers. And remember, we have the two different sides. If we start with the base unit, which is that meters, there's going to be 1,000 meters in a kilometer. And there's going to be 1,000 millimeters in a meter. Now see how there's that 1,000 factor to get us to the meters, and so we're going to be moving that decimal place 3 places just depending on the size of the unit that we're using to measure. So we have 1,000 meters in a kilometer, so 1 meter is a smaller unit of measure than a kilometer, where it's a larger unit of measure than a millimeter. So if we look at this, if we're looking for meters to kilometers, we would want to move the decimal place in a way that would get us a smaller value, because a kilometer measures something that is larger. So we end up with 0.00122 kilometers, and then we end up with 12200 millimeters. So let's look at this again here, a little bit more of a visual. 1.22 meters. If we want to go to kilometers, we'll say this way. We end up with 0.00122 kilometers. And the other way, to a smaller number, a smaller unit of measure is 12,200 millimeters. See how that base unit can change 3 places, 3 decimals this way, and 3 decimals this way, based on milli or killa. Let's try station 2. We're looking at, instead of height or length, we're looking at time. So we have seconds to walk across the room. Let's say it took 24 seconds. Let's do 24.3 seconds. Again, convert it into kiloseconds. It's going to be 0.0243 kiloseconds, or 24,300 milliseconds. Converting one direction to the larger unit and to the smaller unit. I'm going to show you this a different way on station 3. Here, this is conceptually something you have to think about, like, am I going to a larger unit of measure or a smaller unit of measure, and then am I moving the decimal to the right, am I moving the decimal to the left? We can actually do this mathematically as well. So let's say the liter jug, the jug that we had is 3.78 liters, which essentially is a gallon. So if we're going to convert that thing into liters and milliliters, just like we have before, we can do this thing using conversion factors. So we have, we're going to do something called factor labels. So we need the conversion factors that we've been using. 1,000 milliliters is equal to 1 liter, and then we have 1,000 liters. Oops. Let's get rid of that. I'm going to start with 1 liter is equal to 1,000 milliliters, or we could say that 1,000 liters is equal to 1 kiloliter. Now, we usually don't use kiloliters. It's kind of strange to me that that would even be an option. I guess it's not here, but it's part of it. So notice I'm doing things something a little bit different over here. So focus what is going on here. So I want to show you the conversion process. So if you have 3.78 liters and we're going to try to get it to milliliters, you can do this thing called dimensional analysis, where we split things up. Nothing goes here in the box below the value. That's nothing. We can put the conversion. Now, a liter goes down here because it matches the labels, and then milliliter goes on the top. This is like a big fraction, and if you have the exact same thing on the top of the fraction as you do on the bottom of the fraction, they cancel out. So the unit of liter cancels out. 1,000 milliliters is 1 liter, and we can get our answer. We're multiplying it across, we get 3780. Now I'm showing you this because some kids are really math inclined, and this makes a lot of sense. So if this doesn't make any sense, just ignore it for now. We'll come back to this in semester 2, and we do a lot of work like this, but it's not necessary right now. But it's helpful. Awesome. All right, let's get a new page up here. Oofta. Percent error. Percent error is equal to the actual minus the experimental divided by the actual. Take that absolute value and multiply that thing by 100. Simple enough. Contrast accuracy and precision. Accuracy is how close you are to the right answer. Precision is how close the data points are to each other. And so we can look at a couple examples later on. But accuracy, how close to the right answer. Precision, how closely to each other. And the dartboard scenario is one that gets used very frequently for this. Man, this just jumps all over. Bummer. There. Just gotta stop moving that around. All right, the dartboards. So we have the 4 different dartboards. I can't write over here. Sorry, guys. I have to write over here. So I'm gonna do A here. Precise and accurate. We have the dartboard. That would be if we had all of the arrows close to each other and where we want them at that bullseye. So that's precise and accurate. B, precise and not accurate. That would be if all of them hit the exact same place but not where we want them. This happens to me when I play golf. I can very accurately, or very precisely put the ball in the wrong place many times. So I have a horrible slice, and it just ends up going to that same location over and over. It's not where I want, but it happens every single time, so it's precise. C is going to be not precise, but accurate. This is the weird one that doesn't happen very often. But this is if you got data points that weren't precise, that is, they aren't close to each other, but the average of them comes out to be the right answer. And finally, the last one is not precise and not accurate. This one's pretty easy. This is what happens to me usually if I actually play darts, and we end up with things all over the place. And it's not precise, it's not accurate. All right, so let's look at some actual data and figure out if we can determine what is what. So letter A, target value of 3.21, data 3.22, 3.21, 3.20, all of these data points are close to each other, so this is going to be precise. So this is number 4. It is precise. And then all 3 of these data points are also close to the actual value you're looking for, so that is also accurate. So this is A. B, we have 150, 150, 160, 160. These are not precise because they're far away from each other. These 2 are precise and these 2 are precise, but when you put all 4 data points together, not so much. The average, though, of this is going to be 155, so it makes it accurate. The question really comes often is like, well, how do I know how close it has to be to the right answer for it to be accurate? And that's a hard question to answer at this level. What I can tell you is that if it's not accurate, it will be very, very obvious. Like if this came out to be 112, you could pretty well identify that that's not going to be accurate. But 155, 156, something like that, you can say it's going to be accurate. All right, let's go over to the other side. Letter C, we have 300, or wait, yeah, 301, 301, 300, 299. So all these are precise because they're all very close to each other. The target value is 400, not accurate. Last one, 4.25 meters is what we're looking for. 65, 50, 90, sorry, 900, 1. That is not precise. Not accurate. Let's go back and do some percent error work. So I need a new page here. Let's put the percent error equation back up here. Actual minus experimental divided by actual multiplied by 100 gets us the percent error. The language is different. This is actual and experimental. Over here we have target value and data. The target value is what we're after. That's the actual. That's what we know to be true. The data, that comes from doing an experiment. You get data from experiments. So that's going to be the experimental. So we can plug things in and solve. I'll do a couple of these here, but not all of them. I should have said this. So I leave this blank here. It's the average. You're going to average those pieces of data together. So if we look at A, the actual is 3.21. The experimental, if we average those 3 things together, comes out to be 3.21 divided by 3.21 times 100 gets us a 0% error. So I'll walk through that one really fast because it's 0, but these 3 things come out to be 3.21. So actual, 3.21, that's the target, right? Experimental, 3.21, all right? Let's look at B. That's going to give us at least a little bit of a percent error. We have 157 minus 155. Just a review of averages. Add the 4 numbers together, divide by 4, come up with 155. We'll divide this by 157 again, times 100, and get out my calculator. .3% error. Now, if we want to get this really specific, to answer that question I said before, how do you know if it's actually accurate? I'd say anything lower than a 3% error is going to be accurate. Sometimes it depends on the size of the numbers, but 3% or less, we'll call it good. All right. Let's do scientific notation next. Stop. All right. We have two different kinds of scientific notation here. Ones where we have the very large number, and the ones where we have the very small decimal. Scientific notation is used to express large values, either very large numbers or very small values, with lots of zeros, in a more easy way, less cumbersome way. So the way we do this, let's do a 9500000, is to move the decimal place in between the first two numbers, 9.5. Now we're going to multiply this by 10 to the number of the times you had to move the decimal place. The decimal place starts here, 1, 2, 3, 4, 5, 6, 7, so times 10 to the 7th. Same thing with B, 74200000000, between the first 2 points, times 10 to the number of places we move the decimal, 3, 6, 9, 11. So there you go. Letter C, when you move the decimal to the right, it's going to be to the negative exponent. So we end up with 0.0234541113. In between the first two numbers, 113 times 10 to the negative 1, 2, 3, 4, 5, 6. And finally, letter D. 1, oh my goodness. 1, this is hard to do on a screen. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8, 9, 4. 9.4 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Now if I want to go backwards, all we need to do is exactly that. A is going to be, that looks like, not an A. Seriously. So, let's see if we can figure this out. Got it. 7.22 times 10 to the 8th. We're going to move the decimal then out. So if we had to move it to the left to get into scientific notation, we're going to move it to the right to get it out of scientific notation. 7, 2, 2, 1, 2, 3, 4, 5, 6. So I move the decimal place 1, 2, 3, 4, 5, 6, 7, 8. There you go. B, 9.12 times 10 to the third gets us 9120. C, going the other direction, 8.32 times 10 to the minus 7th. Now we're going to move the decimal place to the left. So 1, 2, 3, 4, 5, 6, 8, 3, 2. Moved it 7 places. Started here. 1, 2, 3, 4, 5, 6, 7. Letter D. This one seems kind of silly because of all the numbers, but we have 1, 2, 3, 3, 4 times 10 to the minus 5th. So it comes out to be 0, 0, 0, 0, 4, 1, 2, 3, 3, 4. All right. That concludes the different parts there for accuracy and precision, conversions, and scientific notation. Thanks.